Okay, this video will finish up our introduction to light and matter, the interaction of light and matter. And we left off last time with a practice problem, so hopefully what I want you guys to do with these practice problems is go ahead and just pause videos. In this case, you had to pause, but just to make sure to try to work them out on your own. I spent precious classroom time actually trying to force my students in face-to-face classes to do this because it's very important, right? Just start to get practice putting pencil to paper and trying to work these problems. So I'm going to show you how to solve it now. If you want to pause it, go ahead. Before to solve this, we just need to use the formula for the energy of a photon. Remember, it was given on one of the previous slides. Energy is equal to Planck's constant times the frequency. And remember, we also converted this on a previous question, 632.8 nanometers to frequency. So here it is. So the frequency that we found was 4.74 times 10 to the 14th hertz, or 1 over seconds. To solve it, we just need to use E is equal to h nu. So our energy is going to equal, right, separate out that a little bit, our frequency 4.74 times 10 to the 14th hertz times Planck's constant. Planck's constant was 6.626 times 10. I'll go ahead and write that one as a superscript to the negative 34. And some complicated units there. Kilograms, meters squared per second squared. All right. So remember, kilograms, meters squared per second squared. I have made a mistake in my units for Planck's constant here. Oh, sorry, kilograms, meters squared per second. There we go. All right, that's all we really have to do is just, this is really a question on just, can you set this problem up in your calculator correctly, right? I'm going to ask you to do this on paper. So 6.626 times 10 to the negative 34 times 4.74 times 10 to the 14th hertz. And remember, hertz is just 1 over seconds. So we're going to write that 1 over seconds. And that means we're going to end up with kilograms, meters squared, seconds squared for our units. Okay. So what do we get? All right, if you plug that into your calculator, you should get 3.14 times 10. Sorry, I don't want to try and write with my cursor anymore. So I'll just take my time to do this. 10 to the negative 19. And you get the units for energies, which are joules. Right? So I'm just going to write that out as joules. All right, that's what you should get for the energy of this photon. The frequency was 4.74 times 10 to the 14th. The wavelengths, whatever we had before, 632.8 nanometers. Okay, so you need to know how to use this formula. So it's really just a question of your calculator and setting it up and remembering the units. Remember those units. The units are telling you if you did it correctly. In this case, 1 over seconds combines with these units to give me the units for energy, which is what I wanted to calculate. So your units are helping you to solve these problems. Okay. All right. So why do we care about light in a chemistry class? It seems a little bit, of an excursion into something else. Well, everything we know about atoms is a result, first of all, about being able to see it with our eyes, but also the instruments that we use. All of the modern instruments are mostly using electromagnetic spectrum information from the atoms and the compounds, the molecules, whatever. All right, so everything we know, this is not an exaggeration, everything we know about them is a result of observing how light and matter interact. So I want to talk about, just real briefly, about this seminal experiment, the photoelectric effect. This was what kind of returned us to a more particle-like view of light. And also, when we had quantum chemistry come up, quantum mechanics, it started to allow us to see that not only was light behaving like a particle, but strangely enough, electrons had started to act like waves because they're really, really light, so they're affected by this. But first, let's sort of back up and say, what is the photoelectric effect? Well, experimenters had noticed that when you would shine light on the surface of, say, a metal, that you could, if the frequency was high enough, you could actually eject electrons from the surface of that metal or whatever it was. All right. This phenomenon was called the photoelectric effect, and Einstein was the one who actually explained it. And he said, well, there is the ability of these electrons and the materials to sort of absorb these photons as long as the frequency had reached a sort of threshold frequency. So we need, and since energy is proportional to frequency, we have some threshold energy that the photon needs to meet in order to be able to eject that electron. This is called the photoelectric effect. All right, just a couple of formulas to throw at you. So these are really similar to the previous ones. I don't have any example problems that I'm going to work, but the other slides that I give you on in Blackboard that you'll find, will have some other example problems for you to work, and just get some practice with those. And so I have another slide pack that you have to go through to give you another view, another look at it. But the work function is related to the threshold frequency. So the work is defined as this guy, and you remember that energy was equal to h nu, or in this case we're just defining a new energy. This is the minimum energy needed to eject electrons, and we signify it with this Greek letter. And then we can put this in terms of frequency or wavelength by just substituting in our relationship lambda nu is equal to c. Okay. All right. We can also get the kinetic energy of the ejected electrons by just remembering something, a really simple application of the conservation of energy, just to show you how important those fundamental formulas are, right? Conservation of mass, conservation of energy. We can get the kinetic energy of this electron by just figuring out the incoming energy of the photon that spit it out, and then we subtract off the amount of work that it took, the work function, and we get the kinetic energy of the electron, right? Because whatever's left over, whatever excess energy we had above and beyond the work function, or the minimum amount of energy needed to spit out those electrons, is just going to be left over in the kinetic energy. Okay, so this is the energy of the incoming photon. This is the work energy. All the leftover energy is going to be the kinetic energy put into the electron. It's going to be flying off with this much energy, with the speed associated with that. Okay. All right, that's going to end our kind of review of the photoelectric effect. We're going to move on back to light and matter. So one way that light and atoms can interact is by the atom actually absorbing that light. And what we see when we look at different atoms absorbing light is that they all have a characteristic wavelength or wavelengths that they absorb. These characteristic wavelengths that they absorb amounts to a fingerprint, if you will, for that atom. They are totally unique to that particular atom. And I'm going to give you guys here a really simple model called the Bohr model. So this will be my introduction to the Bohr model. And then we'll talk a little bit more about it. And I want you guys to understand, first off, this is not the modern view of the atom or the electron energy levels in the atom, but that's okay. All right, it's a great first place to start, just to think of it as there are these shells, right, or energy levels wherein electrons dwell or live. All right, you can see here I've drawn a tiny little electron on there. Again, that's not exactly what an electron looks like. This is indicating the nucleus. In this case, it's just a hydrogen atom, and we designate these levels by, or shells, with N1, N2, and N3. So this is the first shell, second shell, third shell. And you can see for hydrogen, just has one proton, therefore one electron, and it's dwelling on this closest shell. We call this the ground state electron configuration for hydrogen, with that electron in the ground state. So each of these shells will fill up with the appropriate number of electrons. They all hold different numbers of electrons. This first shell holds 2. So we can put another electron in this shell, but hydrogen only has 1. And so the ground state is with all of the electrons in the lowest energy that they can possibly get to. For hydrogen, that is with the electron in this N1 energy level or N1 shell. Okay, so this was the model that Bohr came up with. And the reason that we had to come up with this is because the previous models weren't working, right? The previous way that we looked at it did not tell us why we would observe a characteristic wavelength or wavelengths for each atom. That just wasn't part of that theory. In fact, it would make no sense by looking at it the previous theory. The previous theory was that electrons could sort of circle anywhere in here, right? So for the Bohr model, you can only circle here or here or here. But the previous model was that electrons could rotate around anywhere, right? So you could have an electron rotating right out here. Right? It's okay to think of this as the solar system model. Right? So in between these two planets, right, you'd have another one. That was the previous model. The previous model said that they could rotate or circle the nucleus anywhere they wanted. The Bohr model just said, nope, they have certain specific energy levels that they have to dwell in. All right, so when we think about it, each of these levels has a certain energy. And so if I want to take an electron and do anything to it, I'd have to bump it from one shell to the next shell. And when I do that, there's an energy difference associated with that movement, right? That bump is going to require the specific energy to get from shell 1 to shell 2, for instance. The energy is the difference, okay? This is just a normal formula for energy. For the, this to this is just the difference between these two guys. So E2 minus E1 to go from E1 to E2. And then remember that delta E, right? If I correlate that to photons, a photon will have that energy if h times the frequency is equal to delta E. So what we observe is that atoms can only absorb a photon if it exactly matches the transition from one energy level to another. Right? This is what explains the fact that for each atom we observe really specific absorbances, or different wavelengths that they absorb. Right? Because they have electrons in certain specific shells, and to bump it up I have to go that specific wavelength. All right, so that's how this new Bohr model, that's the success that it had, is it was able to predict those characteristic, those fingerprints of the atoms, because they can only absorb certain specific wavelengths of light. So how this would look is you have some photon flying around, right? It has a certain wavelength associated with it. It comes and it hits this atom. Now, if this photon didn't have the right energy, it would literally fly right through, as if the atom or the photon was just invisible they were invisible to each other. But if the photon does have the correct energy, you can sort of see the electron there. Sorry, it's pretty small. If it does have the correct energy, then it can bump that electron up to the next energy level. So this one did, and it had the energy associated with the difference between N1 and N2. So it did bump it up. All right. So hydrogen has several possible energy levels that it can absorb. We can go from N1 to N2, N1 to N3, etc. And then for other atoms, you're going to have other possibilities, and therefore different absorption possibilities. And it's also important to note that each atom having a different number of protons in the nucleus is going to have slightly different shells, at least in the energy differences between them. Okay, so this is what is giving the absorption spectra for each atom, all the different possibilities that you could have. And if they are in the visible portion of the spectrum, then we can see them with the visible light. All right, each spectrum is unique to each atom. All right, so let me tie this to your observations in everyday life. When light goes in and reflects off of something, say this leaf may absorb some energies of light, all right, specific to whatever's in there, the chemicals making it up. Whatever is reflected off is what you see. So you're seeing red light coming off of this. That means that this leaf was absorbing other frequencies other than red, so maybe blue or green, and all you see are the leftover light coming off. Okay, same thing, kind of the same thing is happening with emission spectra. Emission spectrum, an example would be fireworks. So when fireworks go up, there's certain compounds, certain substances in there, and then you give them a lot of energy with the heat from the explosion. And then you see the emission spectrum. So the emission spectrum is kind of the same thing as the absorption spectrum from these leaves, except sort of the opposite. All right, and so the emission spectrum, the absorption spectrum, these are related to the details of the electron energy levels. All right, what does this look like? Well, this graph here is illustrating an absorption. So we shine some light, we have a sample here, and then we measure what comes off of it. This one is illustrating an emission spectrum. Right, we energize this test tube somehow, and then we just look at what comes off of that from this energization, if I could use that word. So the absorption spectrum will show you all of the light minus a couple of peaks. All right, we call these peaks, or areas where it absorbed. The emission spectrum is showing you kind of the flip side of that. It's just showing you the peaks themselves. All right, so they're missing here, and on the emission spectrum they show up. All right, so we see that each atom is going to have a totally unique absorption and emission spectrum, and they're kind of the same thing. All right, just one is sort of the opposite of the other. This one's absorbing, this one's emitting. Here's a couple of examples. This one's for hydrogen. Hydrogen, you see, has 3 obvious peaks. There's another one in here. But you can't see it. Oh, there it is. Has 4 obvious peaks in the visible spectrum. This is just visible spectrum of electromagnetic light. Helium is a little bit more complicated, right? A couple of more lines. By the time we get to neon, we see just a mess of different peaks in there. All right. If we were to look at the absorption spectrum of sunlight, this would be the emission spectrum, we would see most of the wavelengths filled up. But if you expand in enough, you can see that the visible portion of light from the sun is actually missing a couple of pieces. All right, so you can imagine how this happens. The sun has taken a bunch of atoms that are in the core and is energizing them very, very, tons of energy poured in, and so you're getting a bunch of different peaks, and all of those peaks add up to what we see here. But there's still some gaps, even though there's lots of different atoms in there, and we give it a lot of energy. There's still a couple of gaps there. And just a little side note here, blackbody radiation is what you see when you say heat something up very high. As long as you get over a threshold temperature, you'll start to see that glow. We typically only see this in metals because they're the only things that can take that much heat. But this is slightly different than what we're seeing in the absorption and emission spectrums, and I don't want to talk about that much more. So matter, no, that's it. All right, last thing that I want to talk about here is the Rydberg equation. The Rydberg equation is an empirical formula, which means it was just figured out from a bunch of data points. And the Rydberg equation works exactly correctly for hydrogen, and then you can kind of use it as an approximation for the alkali metals, right? So those are the things that are under hydrogen on the periodic table. So it's a mathematical fit of experimental data, which we call that an empirical formula. And you need to know the equation. You need to get some practice using it. I'm just going to show it to you. I'm going to ask you to go get some practice working with it in the homework. And the equation looks like this. So the general equation is 1 over the wavelength is equal to r, which is a constant. Z is the atomic number of the atom that we're dealing with, z squared. And then we have 1 over n1 squared and 1 minus 1 over n2 squared. Remember, n1 and n2, these are the energy levels that electrons can live in. So we can calculate the wavelength, and therefore we can get the energy of electrons from hydrogen exactly using Rydberg, and as a good approximation for all the alkalis using this Rydberg equation formula. So these are integer values, right? N1 would just be 1, N2 would be 2, and then you square them. This is general, right? So it could be N1 could be N3, N2 could be N4, whatever, right? So we can go transitions up or down in energy. It's just going to change the sign. And then that'll give us the wavelength, and then we can get the energy from that. An alternative form looks like this. This is just for hydrogen, right? We've already plugged in r and z squared here. And then you just plug in the different values that you're going to use. You're going to use this in one of your labs, so I've put it in here for you. Delta E is equal to minus 2.178 times 10 to the 18 joules times the information from the energy levels. So get some practice using those. And right, you see, this is a little bit of algebra to use this. It's not terribly complicated. And you'll see those on the homework and the practice slides. Okay. All right. In summary, the colors of the absorption and emission spectrum are given as a result of electrons either going up a level or down a level. And then quantum mechanics is what we use to explain why all of this is happening. Okay. The value of quantum mechanics is the ability to predict the chemical properties of atoms and molecules. So it allows us to predict behavior, and therefore it's important. Okay. And we're going to finish on that on the next video. All right, so you guys have a good day.